Hello. Can you guys hear me? Can someone confirm, please?
Yes, we do.
Okay. All right. Welcome to the session on design automation. Good morning, good afternoon, good evening to all of you, depending on wherever you are in the world. My name is Abhya Das. I'm from Synopsys, USA. Today in this session on design automation, we have 5 interesting papers. From the logistics point of view, everybody will be muted now, and I'm gonna play the first video. And after each video, maybe we can take a couple of questions. And I believe the presenter is here, so feel free to type your questions in the chat window. And after the individual videos, the presenter can unmute himself or herself and answer those questions. And then we'll go to the next video. So with that, let me play the first one. And the author is actually going to introduce in the video itself. So I'm not going to introduce the first one. All right, here we go.
Hi everyone, my name is Wentian. I'm a PhD student at the University of California, Riverside under supervision of Professor Sheldon Tan. Today I'm going to introduce the EM-GAN model, which is a fast stress analysis method for multi-segment interconnect based on generative adversarial network. First, I'd like to quickly go over some basics about the electromigration. So the electromigration, which is also known as EM, is a physical phenomenon of the migration of metal atoms along the direction of the applied electrical field due to the momentum exchange between atoms and the conducting electrons. With the development of VLSI circuits, the current density increases and the size of the interconnects decreases rapidly, which leads to serious reliability problems induced by electromigration. The EM-induced stress along the metal wire increases as time passing by. When the stress reaches the critical level, a void nucleation appears, which leads to reliability problem. There are many models proposed to describe electromigration, and the Kohonen equation, which is a physics-based model, is widely accepted. Many methods have been developed to solve this Kohonen equation, and they can be divided into 2 categories. The first one is numerical method, which includes FEM and FDM. These methods can be used for general interconnect trees, but they are quite time-consuming. The second ones are the analytical methods. These are more efficient ways, but they can only be applied to specific interconnect trees. This figure shows the flow of how we can derive the EM-induced stress distribution. The input circuit design is given to the numerical or analytical solver, and the result is a time series of outputs, which reflects the evolution of the stress as the aging time increases. In this work, we propose to treat this traditional problem as an image-to-image transformation process so that we can leverage EM-GAN, which is a machine learning-based generative model, to substitute the traditional ways with the hope that it can be applied to any general interconnect trees, but still achieves high efficiency and accuracy. The reason that we use GAN as the backbone of our model is that it has been proved to be effective in all kinds of image generation applications, such as figure-to-figure, draft-to-figure, and even text and sound-to-figure transformation. So why can't we use it to convert the interconnects with current densities to the stress distribution images? Just like the other machine learning models, sufficient training data is always a must. To get the training set, we first randomly generated some interconnect topologies, and the current densities in each wire segment are also randomly produced. Both of these inputs are given to COMSOL, which is a commercial FEM solver, to produce the ground truth stress results. In this work, we set the time step here to 1 year, and the maximum aging year is set to 10 years. So for each input, the output are 10 stress results representing the stress evolution from the 1st to the 10th aging year. The problem here is that both input and output data are still saved in numerical formats. To leverage the EM-GAN model, we have to convert both of them into images. To transform the input data into an image, we first project the interconnect topology onto a grid, which has a resolution of 1 micron. After that, the current densities are filled into the wire segments so that the final input image is a heat map of current densities. Same conversion is also applied to the output. The only difference here is that stress values instead of current densities are filled into the topology image. Now we transformed both input and output data into images so that we can leverage the EM-GAN model to learn the transformation from the input topology to the output stress maps. We finally generated 2,500 random topologies for the training set, and these are some examples. As you can see, for each input topology image, there are 10 output stress maps corresponding to it. This is the framework of our proposed EM-GAN model. The generator takes the topology image as input, but as I mentioned in previous slides, each input topology has 10 stress results. To solve this problem, we add an additional aging time input to indicate which year of the stress result is expected to be produced. This time input is then duplicated and expanded into a matrix, which has the same size of the topology image, and then both of these inputs are combined into a two-channel image. Then the generator will do some transformation to convert the input into the estimated stress map. The generator has an encoder-decoder structure, and we also added skip connections to directly transfer the high-level topology information from the input to the output. This actually helps a lot to improve the final results accuracy, and I will show the details in the discussion part. Then the generated stress map or the ground truth from the training set will be taken as the input by the discriminator. The topology image and the aging time is also given to the discriminator as conditional input, so that the discriminator is trained to judge whether the input stress map is the correct solution to the given topology at the specified aging time. The output of the discriminator is taken into the calculation of the loss functions. One thing I'd like to mention here is that the generator's loss function is actually not only determined by the discriminator. As you can see here, we also added the L2 norm loss, which also helps to improve the final results accuracy. For the training of the EM-GAN model, we randomly selected 15% of the dataset for testing purpose and used the remaining 85% to form the training set. The model was trained for 15 epochs, and our test results show that the EM-GAN achieves an average root mean square error of 0.13 gigapascal. This seems to be a quite large value, but when you consider the full range of the stresses, as you can see in the color bar, the stress value usually varies in the 2 gigapascal range. So if we calculate the normalized RMSE, which is the RMSE divided by the full scale, then the average error is only 6.6%. And when we take a closer look at the junctions and terminals where the stress usually accumulates, these two results are estimated by EM-GAN, and these two are the ground truth. We can see that both results agree very well with the ground truth. Then we compared the inference speed of EM-GAN against the state-of-the-art work, which is an analytical method. We ran both methods on more than 500 testing cases, and the total time cost of EM-GAN is 4.58 seconds, and the state-of-the-art work costs 37 seconds. So EM-GAN achieves 8.3 times speed up. But we have to admit that the state-of-the-art work actually achieves better results accuracy, but the time it costs to solve each case is determined by the number of branches, which means that it costs much more time when the interconnects get complicated. While this is not the case for the EM-GAN model because every input is taken as an image with fixed size. So this is actually another advantage of EM-GAN, since the inference speed is always fast, even when the topology gets super complicated with a large number of branches. As I mentioned before, we added skip connections in the EM-GAN's generator and also introduced L2 norm into its loss function. To see how these modifications can be helpful in the results accuracy, we trained 3 different models and compared their inference results on the same test set. As you can see in this table, the first model is the EM-GAN, which has both skip connections and L2 norm in the loss function. The second one only keeps the L2 norm but removes the skip connections. So the result's accuracy is much worse than EM-GAN. The third model keeps the skip connections but removes the L2 norm. The accuracy is better than the second model, but still worse than EM-GAN. This result can also be verified by these stress maps. To sum it up, in this work, we first show that EM analysis modeled by partial differential equations can be viewed as image-to-image transforming process. We then explore the conditional GAN structure in which the input images, which are the multi-segment interconnect topology with current densities, are treated as conditions. To solve the time-varying stress modeling problem, we further add the aging time input as a continuous condition for both generator and discriminator in our proposed EM-GAN model. Different structures of GAN were studied and compared. The resulting optimized EM-GAN can quickly give accurate stress distribution of any multi-segment interconnects at a given aging time. Our test results show that the EM-GAN has 6.6% averaged error compared to COMSOL results and achieves 8.3 times speed up over recently proposed state-of-the-art analytic-based EM solver. So that's pretty much for my presentation, and thanks for listening.
Thank you, Wentian. If anyone has questions, please type it in the chat window. And Wentian, we as I said, we have time for maybe a couple of questions. Wentian, can you look into the chat window, and if there is any questions, please answer that.
Yeah, sure. Thanks, Sabia. So your question is, the accuracy of our model seems still not very satisfactory compared to the traditional method. So why is it that, and is there any possible ways to improve it? So thanks for your question, Sabia. So as I mentioned in my slides, our absolute value of the error is 0.13 gigapascal, which seems to be very large. But when you consider the full range, it actually usually, it's not like the traditional image, which is bounded between 0 and 255. So in this stress problem, the stress usually ranges from negative 2 to positive 2 gigapascal. So when you consider the full range, it is actually only 6.6% normalized RMSE error. And but yes, I have to admit that compared to the traditional method, it is not very accurate. So one possible way is that to increase the training set. This is a standard way to increase the accuracy of the machine learning models. And the other way is that we are thinking of making training several different models for different ranges of the values, so that the final results can be combined by these ensembles of models. And we hope that this can help the final accuracy increasement. Thanks.
Okay, sounds good. Thank you. So we will now move to the second presentation. It's the title is Maximum Click-Based Method for Optimal Solution of Pattern Classification. Okay, let me share my screen. And
everyone, my name is Xu He from Hunan University, China. Today, I will introduce a pattern classification method, which can obtain optimal solution based on maximal click. This is outline. Firstly, we give the motivation and problem formulation of layout pattern classification. Then, we give the overview of our method and discuss our techniques in detail. Finally, we do experimental result comparison with previous works. The motivation. With the continuous shrinking of future size, design for manufacturability DFM has risen as one of the major concerns in semiconductor process. Layout pattern classification, which group geometrically similar layout clips into clusters, has been widely used in a variety of DFM applications. This is the problem formulation of pattern classification. The input is the layout in GDS2 format, which contains layout, polygon patterns, and markers. A marker is a polygonal region, which indicates a hotspot location. A clip is composed of a set of rectilinear polygons, with a marker contained in it. In our work, the clip center is set to the center of its corresponding marker. The objective of the pattern classification problem is to minimize the number of clusters to group the clips under a given similarity constraint. In our work, we apply the same similarity matrix as in the ICCD 2016 contest. The similarity matrix include ACC and ECC. For ACC criteria, it checks the area difference between clips. And for the ECC criteria, it checks the maximum shifted distance of edges. This is our framework. Given input layout and similarity constraint, we first do clip data preparation and obtain all clip information. After data preparation, we do maximum clip-based clustering, and this is our major part. Firstly, a clip association graph is built by checking whether the similarity constraint is satisfied or not between each pair of clips. Then we call maximum clip to compute the lower bound of cluster number. Finally, we transform the pattern classification problem into a set covering problem and utilize the result of maximum clip to accelerate the convergence of the set covering problem and give the output. Here, we briefly introduce the data preparation process. The rectilinear polygons in the layout are firstly partitioned into rectangles. Then the rectangles overlapping with clip regions are extracted. Additional rectangle merging is performed for each clip. After obtaining all clips, we merge the identical clips to reduce the problem size. In the process of maximum clip-based clustering, for each pair of clips, we first compute their similarity distance under the ACC criteria or the ECC criteria. Take clip CI and CJ as the example shown in the figure. For ACC criteria, XOR operation is called to obtain the different parts. The distance of clip CI and CJ is the overlapping portion of their area difference. For ECC criteria, we do clip minus operation first. This figure gives the example. The result of clip CI minus clip CJ is the actual path in CI compared to CJ. On the other hand, the result of clip CJ minus clip CI is the actual path in CJ compared to CI. If the actual paths in each clip can be removed by edge shifting, and the maximum distance of edge shifting is less than the given ECC constraint, we say that the two clips CI and CJ meet the ECC criteria. In our work, instead of doing edge shifting, we apply clip enlarge and clip shrink operations, which is easier to implement. After computing the similarity distance between each pair of clips, we can build the association graph G. In the graph G, the node set is the clip set. If two clips CI and CJ can be assigned into the same cluster, there's an edge. For two connected clips, if their distance is less than the similarity requirement, this edge is called direct edge. On the other hand, if the distance of two clips CI and CJ is larger than the similarity constraint, but exists a clip CK, and it meets the similarity requirement with both CI and CJ, these three clips, CI, CJ, and CK, can be assigned into the same cluster by setting the clip CK as the representative clip of the cluster, and the edge connecting CI and CJ is called indirect edge. After building the clip association graph, we generate its complement graph. Each edge in the complement graph means that the connected clips cannot be assigned into the same cluster. Then we call the maximal click on the complement graph. The number of clips in the maximal click set is the lower bound of cluster number, and the proof is given in proof 1 in our paper. Since the maximal click problem is the NP problem, if heuristic algorithm is used to solve the maximal click problem, its result is still valid at the lower bound of optimal cluster number, and this proof is given in proof 2 in our paper. At last, the clip clustering problem is converted into a set covering problem, whose objective is to minimize the cluster number. Although some previous works have also formulated the clustering problem as a set covering problem, we summarize the difference here. Firstly, we introduce the result of maximal click to do initialization. Secondly, we have proved and adopted an optimal solution as the ending condition to accelerate the convergence of the set covering problem. The following experimental results show that our method is more stable for large benchmark, and the clustering results are optimal for all benchmarks. The benchmark shoes from the ICCD 2016 contest are used for the performance evaluation. Here, we give an example of clustering process of benchmark case 2. In the finger A, each node is a clip in case 2. For each pair of clips meets the similarity requirement, there is a director edge connecting them. Finger B is the association graph G. Based on the director edges, we can add indirect edges in finger B. The complement graph of the association graph is shown in finger C, and the connected clips in finger C cannot be assigned into the same cluster. We do maximal click on the complement graph, and the result is given in finger D. Finally, the clustering result after solving the set covering problem is shown in finger E. Since the cluster number is equal to the number of clips in the maximal click set, the obtained clustering solution is optimal. This figure presents the runtime breakdown on average. In our implementation, more than 17% of the runtime is spent on the clip data preparation. The runtime for maximal click computation is almost negligible, and the SCP clustering process is only about 2%. In this figure, we compare the runtime of original SCP and our maximal click-based SCP. It can be seen that our method is faster for all benchmarks. This is mainly due to the maximal click-based initialization and ending condition. We compare our result with previous works in this table. It can be seen that our cluster number is equal to the lower bound for all benchmarks. Therefore, our proposed method can achieve optimal solutions for all benchmarks. Besides, we also reach the largest cluster size for all benchmarks as well, and our runtime is approximate minimal runtime.
Can you guys hear me? Sorry, I had an audio issue. Thank you, Sue. If you can answer the question I typed in the chat, that will be good.
Yes. Thanks for the question. The question is the input cluster result obtained by solving the set covering problem, or is there any post process to do refinement? Thanks for the question. And my answer is that after solving the SCP, the set covering problem, the number of clusters, and the representative clips of each cluster are obtained by SCP. But we still have many remaining clips, which is not assigned as set as representative clip. And for each remaining clip, we assign it to its associated cluster with the largest number of clips. By doing this, we can further maximize the largest cluster size and further refinement our result. That's all. Thanks.
Okay. We'll move to, thank you. Our next speaker is Vladimir, and the topic is adaptive simulation with virtual prototypes for RISC-V, switching between fast and accurate at runtime. Let me start the video. Sorry. What happened to my Zoom? Oops. Do you see my screen?
Okay. My name is Vladimir Herd. I'm from the German Research Center for Artificial Intelligence, or DFKI in short, and my talk is titled Adaptive Simulation with Virtual Prototypes for RISC-V, Switching Between Fast and Accurate at Runtime. I want to start with a brief motivation on virtual prototyping. So a virtual prototype, or just VP in short, is essentially an executable, abstract software model of the entire hardware platform. VPs are leveraged for early software development and other system-level use cases in the design flow. A key feature of the VP is that the VP is binary compatible with the real hardware platform. That means the same software binary can be executed on the VP and the real hardware platform without any modifications. VPs are an industrial-proven solution and predominantly created in the standardized System C modeling language using the transaction-level modeling methodology. VPs are leveraged for different use cases. One important use case is functional validation of the software early in the design flow. Another important use case is a performance evaluation. To support these use cases, different requirements need to be met. For functional validation, a very high simulation performance is a key requirement to boost the overall validation process. For performance evaluations, on the other hand, a simulation with timing-accurate results is mandatory. These requirements are actually conflicting with each other, and thus there is a trade-off. A possible solution is to create different VP platforms for these use cases. However, this becomes quickly inefficient as only parts of the software may need to be analyzed with accurate results. To deal with this problem, a VP-based adaptive simulation can help by enabling to switch between a fast and accurate simulation setting at runtime on demand. In our paper, we present such an adaptive VP-based simulation for RISC-V-based systems. We focus on switching settings in the instruction set simulator, or in short ISS, of the VP. Therefore, we provide an interpreter-based setting as foundation for an accurate simulation and a JIT-based setting to achieve a very high simulation performance in the VP-based setting. Both interpreter and JIT operate on the same execution state. The execution state includes the register bank and the program counter. By operating on the same state, it is possible to switch between interpreter and JIT-based settings very easily at runtime, as the execution state always remains consistent. The ISS uses a memory interface to perform memory access operations. These are packed into TLM transactions and routed through the TLM bus to either a memory or peripheral. DMI, a common optimization for System C-based simulations, is used to speed up memory access operations by bypassing the bus system. An MMU is integrated to translate virtual to physical addresses. A timing model is periodically updated to measure the simulation time. For optimization purposes, a TLM quantum keeper is leveraged. Finally, the JIT-based setting generates native host machine instructions by translating the guest RISC-V instructions. It operates at a granularity of basic blocks. We have implemented our approach on top of our open source RISC-V VP. The VP is implemented in systemcTLM and available under MIT license at GitHub. This slide shows the performance evaluation results using the EM-Bench benchmark set. Besides 4 VP-based settings, we also added other RISC-V simulators such as QEMU and Spike to this evaluation. The table on the right side shows the average MIPS on the whole benchmark set. The graph on the left side plots the obtained MIPS per benchmark. A VP-based simulation with link optimizations shows very strong results. It can be more than 500 times faster than an accurate interpreter-based setting and even shows competitive results to QEMU, albeit the System C-based simulation overhead. In the second experiment, we consider a Linux-based embedded application. A kernel driver is provided to interact with peripherals. The goal is to accurately analyze the userland application. Therefore, the Linux boot process is uninteresting and can be skipped. By using a JIT-based setting for booting, we are able to reduce the simulation time by a factor of 24. So in summary, we presented an effective adaptive VP-based simulation approach for RISC-V-based systems. Our experiments show that more than 500 times speedup is possible with a JIT-based setting. Finally, you can find more and related information on our RISC-V-based approaches at systemc-verification.org/RISC-V. RISC-V-based approaches at systems.
Okay, thank you, Vladimir. If you can please answer the questions, that will be good.
Yes, sure. So there's one question in the chat. How is the switching between different accuracy settings realized? And in general, we have like 2 options to implement the switching. And one is basically to pass a specification, which is checked at runtime. The other is basically embedding the switching commands into the software. And passing a specification is more flexible, but it's also more performance intensive because you really have like to check after every instruction if you need to implement a switching command at runtime. So therefore, we use the approach for embedding the switching commands into the software. It gives you very precise control in combination with a high performance because we really use designated switching instructions basically. And instead of using special RISC-V instructions, we implemented it using eCall instruction. And this one allows you to perform a system call. This is a special instruction for RISC-V, and arguments can be passed through registers. And by doing so, we don't need any further instructions, so we don't have to extend a decoder, for example. And this is the way basically how we implemented it.
Okay, thank you. Let's move to the next presentation. This is from Marcos, and the title is Throughput-oriented Spatio-temporal Optimization in Approximate High-Level Synthesis. All right, let me play the video.
First of all, thank you for watching my presentation. This work is titled Throughput-oriented Spatial-temporal Optimization in Approximate High-Level Synthesis. So, approximate high-level synthesis tools have been proposed in recent years to help designers in managing the complexity of exploring approximate computing techniques. Those techniques exploit the resilience of many application domains to imprecise results, including signal and multimedia processing, machine learning, computer vision, data mining, and many others. The idea behind this approach is providing benefits in design metrics such as performance, area, and energy, with a minimum deviation from the exact design. Therefore, you can use approximate AGLS tools to relieve the costs of high-performance accelerators while avoiding the development time and complexity of handcrafting approximate circuits. However, the methodologies proposed so far do not target throughput optimizations, being instead focused on optimizing more specific design metrics like area, delay, and power. Here you have an example of how we can use approximations to increase the performance of throughput-demanding applications. First, we define an accelerator architecture composed of input and output buffers, control logic, and 4 processing units with a given area and processing delay. Note that interconnections are omitted for the sake of clarity. After approximating the PU, area and delay are reduced, and thus the throughput can be improved by increasing the reuse over time, at the cost of introducing output errors. But in fact, we can use the area saved to further boost throughput by using more PUs in parallel while sustaining the quality of results. Going further, we can apply more aggressive approximations to reduce even more the area and the delay of individual PUs at the cost of degrading the output precision. Therefore, from this example, we can conclude that area and delay optimizations should be explored in conjunction when targeting throughput optimizations. Following this brief motivation, I will present how we perform throughput-oriented approximations, our design methodology, the experimental setup and results, and finally the conclusions. Here we have an overview of our design methodology. It automatically explores approximations for yielding parido-optimal accelerators in terms of output errors and throughput, given an area constraint, or in terms of error and area, given a throughput constraint. The inputs are the PU description in a high-level language and a set of representative inputs for training and quality evaluation. The output is a set of approximated PUs described in HDL code and ready to be synthesized down to a hardware platform like ASICs or FPGAs. As you can see, the methodology is divided in 4 major steps. Given the PU source code, the first step is using the HLS front-end to generate an intermediate representations IR code suitable to be optimized by transformations provided by the compiler toolchain. In the second step, we iteratively transform the IR code through an optimization heuristic that eliminates operations with variable to constant substitutions, V2C. This technique replaces arithmetic and logic operations with constant values previously profiled with code instrumentation. After each approximation step, we also perform traditional compiler optimizations that can be enabled by such replacements, such as dead code elimination, constant propagation, and strength reduction. The design heuristic explores both area and delay optimizations, enabled by selectively applying variable to constant substitutions. At this point, area, delay, and error metrics are estimated, and the design with best fitness is selected according to a function that evaluates error and error delay product trade-offs. Next, in step 3, the selected design is processed by the HLS backend and the device-specific synthesis tools to obtain precise area, delay, and energy metrics. The final error metric is obtained with a set of test inputs disjoint from the training set. Note that steps 2 and 3 can be iteratively repeated to obtain progressively approximated designs. Finally, in step 4, the final accelerator architecture is built following the global system constraints. For example, given the available area, the designer can choose the most appropriate error throughput trade-off, or, given the required throughput, choose an adequate error area trade-off. Now I will present our design heuristic with more details. First, we fully synthesize the exact PU code to get the exact area, the maximum frequency, and the schedule information. The design metrics are provided by the target-specific synthesis tool, and the schedule information is provided by the HLS backend. Next, the exact PU code, which is the parent design at the first iteration, and its schedule and the maximum frequency are provided to a static use case execution time analyzer. This analyzer is based on the implicit path enumeration technique used in state-of-the-art time analysis tools. The output is the worst-case execution delay and the time-critical execution path. That is, we have the basic blocks belonging to the critical path and their execution count. At this point, we save the parent design as a possible solution and yield new approximate designs by applying variable to constant substitutions, followed by standard compiler optimizations. This process is repeated for each operation in the parent's critical path, one at a time. In the next step, we characterize each approximate design resulting from the last step regarding area savings, delay savings, and error metric. Delay savings are estimated by using the schedule information and the basic blocks execution counts. More specifically, we calculate the difference between the height of the data flow graph before and after the variable to constant substitutions, times the execution count of the basic block that the operation eliminated belongs. On the other hand, area savings are estimated by verifying the area usage of the operations eliminated in the device characterization file, in the case of FPGAs, or in the technology library, in the case of ASICs. Error metrics are estimated by compiling the approximate IR codes with the x86 backend and executing them using the set of training inputs. With all approximate candidates and their design metrics at hand, we select the parido-optimal design with the highest fitness to forward to the next iteration. To define the fitness function, first we need to define the area delay product savings, ADPS, which is the product between the relative area savings and the relative delay savings. That is, the area and delay savings relative to the parent's area and delay, respectively. Finally, the fitness function is defined as the product between the area delay product savings and the relative error measure. The parido-optimal design in terms of area delay product savings and error metric with the highest fitness is then defined as the new parent design and synthesized to obtain exact design metrics and the new schedule information. The last step is verifying if there are more iterations to perform, which is user-defined. If not, a set of parido-optimal accelerators is built using the parido-optimal designs generated by each iteration, respecting the area or throughput constraint. Before presenting the experimental results, we must define the experimental setup. To evaluate our methodology, we used the LEGAP HLS2 as a case study. It targets FPGAs and is built over the LLVM compiler framework. We synthesized a set of 6 benchmarks from signal and image processing application domains for the Intel Cyclone 5 FPGA. The table shows the kernels along with the implementation results for the exact circuits, while the figure shows the relation between error and throughput for 10 iterations. That is, we generate 10 parido-optimal designs for each kernel in terms of mean squared error or peak signal-to-noise ratio, respectively, and the normalized throughput considering a same area over the exact implementation. As expected, these throughput gains come at the cost of a loss in precision. For example, the ADPCM kernel, it is possible to have a normalized throughput of 1.35 with about 250 of IMSE, or 1.6 of throughput with about 465 of IMSE, depending on the designer needs. Or, for the motion kernel, it's possible to have a normalized throughput of 1.12 with about 30 dB of PSNR, or a throughput of 1.25 with about 25 of dB of PSNR. As our tool optimized for both area and the delay to increase throughput, we also can attain sensible energy savings. The figure shows that energy is proportionally reduced with the area delay product for all kernels, as expected. This figure shows for each kernel the throughput error trade-offs achieved when ADP, area, or delay is optimized. As can be observed, considering both area and delay optimizations enables throughput gains for all scenarios with negligible difference in mean squared error or peak signal-to-noise ratio. Thus, we can achieve sensible throughput improvements without additional costs and with equivalent error by using an appropriate optimization target. Thank you for your attention. For all scenarios with negligible.
Right. Thank you, Marcos. If you can please answer the question, that will be good. Marcos, can you please answer the question?
Can you hear me?
Yes, now I can hear you. Go ahead.
Okay. The question is the approach only valid when we do variable to constant substitutions, or given a throughput requirement, the methodology can provide feasible solutions to PU requirements? Well, in fact, the framework is built in a way that any approximate technique capable of reducing area or delay can be used. The reason is because we evaluate the effect of approximations and the IR code before and after the approximation. So
I'm glad to present our paper, Learn to Floor Plan Through Acquisition of Effect.
Oops.
Oops.
Oh, I'm sorry.
No problem,
I'm sorry.
no problem.
Yeah. Okay.
I can repeat, no problem.
Yeah, please. Yes,
So
please continue.
The reason is because we evaluate the effect of approximations in the IR code before and after the approximations. So we can compare the IR codes to find modified or eliminated operations and estimate area or delay savings based on those changes. So you're not stuck on variable to constant substitutions, of course. Future works include implementing new approximate techniques and heuristics. That's it.
Okay, sounds good. Thank you. Our final presenter of the session is Zolun, and the topic is Learn to Floor Plan Through Acquisition of Effective Local Search Heuristics. So I'll now play the video.
I'm glad to present our paper, Learn to Floor Plan Through Acquisition of Effective Local Search Heuristics here. I'm the speaker, Zhuo Lun, from the Chinese University of Hong Kong. So floor planning is a classic problem. So for floor planning, it basically determines the location of the large blocks in order to minimize area, wire length, and so on. So in a typical workflow, we usually first design a dedicated data structure to encode the geometric relationship of the blocks, and then perturb the encoding to generate new solutions. So this is typically a local search algorithm. In this work, we try to enhance the local search method. So how to enhance? Existing works usually adopt a local search algorithm, and then they try to select a good start point, to tune search parameters, to scale the regularization term, or to switch between the heuristics on the fly. We want to take one step further. Our aim is to acquire a local search algorithm from the scratch. So the intuition behind is that prior human knowledge might mislead the learning. So we avoid to introduce too much of this kind of prior knowledge. We will use reinforcement learning to learn a heuristic. So here is our problem description and also the corresponding reinforcement learning formalization. So in our setting, there will be an agent walks in the search space. So in RL, each state is a complete floor plan solution. The task of this agent is to select the neighbor or to reject to move. So if it selects a neighbor, it will get to the new neighbor state. And if it rejects to move, it will just stay at the original state. So in reinforcement learning, the available actions include the defined perturbations and to reject. And here the transition is deterministic. There will be no randomness here. So our task is to optimize the agent's decision based on the signals given by the environment. So in reinforcement learning, we usually call it the reward. So the reward is basically given by delta cost. That is, whenever an agent finds a better solution, it will receive a positive reward. So the difficulties here mainly come from the large state space and also the action space. We will first deal with the large state space. In our practice, we use sequence pair to encode the floor plan. So obviously, the state space is exponential here because we have two permutations of the n blocks in the sequence pair, and also all the blocks can be rotated or flipped. It makes the tabular methods infeasible. That is, we cannot build a very large lookup table and store the optimal actions for each of the states. Instead, we will use a neural network to approximate the policy. So for the neural network, the input will be all the features concatenated into a 1D vector. And the output is always a scalar as the action value prediction. So given the input and outputs, we decided to use a simple multi-layer perceptron as the main architecture. Actually, the action space is also very large. So recall that possible actions include perturbing the sequence pair and to rotate or flip the blocks. So here, the action space is actually n cubed, where n is the number of blocks. So they are all discrete actions. So first of all, the action space is not fixed. The space size is polynomial of the problem size. And in our problem, evaluating an action is actually very expensive because we need both to calculate the energy of a state and to run the 4 parts of the neural network to get the action value prediction. So this is very costly. So our solution is to sample actions in both the training stage and the testing stage. And we also prove that the DQN algorithm still converges in such action sampling setting. Here we show our training result. So the first benchmark is the MCNC benchmark. And we compared our agent with a carefully tuned simulated annealing algorithm. So our task is to reduce both the area and the wire length simultaneously. So as can be seen from the table, our method outperforms the SA algorithm in all 5 cases. The solution is up to 2.5% lower cost, and our agent actually searches much faster. The speed up is up to 5.7 times. And we also conducted experiments on a larger set of circuits called GCRS. So due to the very long runtime, we include early stop mechanism for both the algorithms. For simulated annealing, if there is no move accepted in the last 20 temperatures, the search will be stopped. And for our agent, if there is no better solution found in the last 100 steps, the search will also be stopped. So as can be seen from the table, our method shows comparable performance as simulated annealing. However, we also observe that it runs slower in the larger instance, for example, the M300 circuit here. To comprehend the behavior of our agent a bit, we visualize the search progress. Here is the figure of it searching the M300 circuit of both algorithms. So since simulated annealing is a randomized algorithm, so when the temperature is high, it looks like it goes here and there, and it converges as the temperature going down. And for our agent, it searches in a much smoother way. So our interpretation here is that our agent learns a more greedy and deterministic heuristic. And to understand the runtime in detail and for potential speed up, we also profile the runtime for both algorithms. So as can be seen from this pie chart, so more than half of the runtime is always spent on wire length calculation. So together with packing, we see that solution evaluation takes most of the runtime in both algorithms. So in simulated annealing, it takes 89.2%, and in our agent, it takes more than 75% of the runtime. So in both algorithms, random sampling only takes a little portion of time. So it's around 1 or 2%. To summarize, we targeted the floor planning problem, and our main motivation is to learn new algorithms without human expert knowledge. To do with this, we formulate the problem as a local search problem, and an agent learns how to select among its neighbors. So we propose deep Q-learning algorithm with action sampling and achieve good results on the benchmarks. And we also expect more research along this line. That's all for my presentation. Thanks a lot for listening.
Thank you, Zolin. I have a question which I entered in the chat. Can you please answer that? You have to unmute yourself.
Yes, so can you hear me?
Okay, I can hear you. Yes, go ahead, please. Yes, Zolin, go ahead. I can hear you.
Right, so perhaps the internet connection is not very stable. So thanks for the question. The question is that what kind of features are used as input? So basically we have three sets of inputs to the neural network. So the first set of inputs are related to the energy, because the central goal of the local search is to find a state with minimal energy. So we provide several energy related statistics, for example, the current energy and the energies among the neighbors. And also to represent how a move affects the whole floor plan, we will provide some statistics related to the effects. For example, how many blocks will be affected after this move, and also what are the area of these blocks. And also, since it is a local search algorithm, so we think it is also important to know where the search progress is. So we also provided the search progress here. So here are the three sets of features used in our training. Thanks.
Okay, thank you. I guess that concludes our session. Thank you very much, everybody, for attending the session and the presenters for presenting. I will look forward to seeing you all or most of you in the other sessions of the day and tomorrow. Thank you. Have a good one.